So today we will be continuing our discussion on the language Verilog. So if you just recall that in our last lecture we had looked at some typical Verilog programs, codes, and we had seen, for instance, how we can declare a variable. So we had said that we can have a variable of two types, net type and register type, and depending on the way we are using it, it can be synthesized into either an interconnecting wire or into a storage element like a register or a latch. And we also looked at how we can define a constant value in an expression. So continuing from that point onward, today first we shall see that how we can define a named constant, a constant with a name. Now in Verilog it is called a parameter. So a parameter is a constant which can be defined against a name, and that name can be used in an expression. For example, these are ways in which you can define a parameter. For example, hi high equal to 25, low low equal to 5, or parameter up equal to 0 0, this down equal to 0 1, steady equal to 1 0. You can define like this. In the Verilog code, instead of writing 0 0 0 1 and 1 0, you can refer to them by up, down, or steady. Okay. Now here one characteristic of this parameter type is that you do not specify the size of the parameter when you define it in a name. Now the size gets decided from the constant which gets assigned to it. Okay. For example, in this case, high equal to 25 or low equal to 5, here you can find out easily that high can be represented in 5 bits, low can be represented in 3 bits. So this, the value of the constant will determine the size of this constant, how it will be mapped into the actual hardware when it is actually synthesized. But in some cases we can simply define a parameter, the value will be coming from outside, it is something similar to a global variable. So there by default the size is taken to be 32 bits, because inside the module you really do not know what is the value that will be assigned. Okay, fine.
But in this case the size of high and low is 5 and 3.
Yeah, in this case if you specify the value, you can easily determine how many bits you require to represent that. Here it will be 2.
So that will be 32 bits if nothing is.
If nothing is specified, by default it is 32. Yes, if it is not initialized, it will be taken to be 32. Okay. Next, let us come to the different logic values that you can use in specifying for simulation or for synthesis. Now in Verilog, these 4 are the logic values which are used. 0 means logic 0, 1 means logic 1, x and z, z means the high impedance state, and x is a state which is not known, it is an unknown state. Okay. So unknown and high impedance are different. So actually when you say that the state of a line is at high impedance state, you know for certain that the driver of that line, this has a tri-state capability, and that tri-state control is currently disabled. So this line is really at a high impedance state. But when you say it is x, you really do not know what value the line is at in 0 or 1. Okay. So there is a difference. And for the purpose of simulation, this is for simulation only. So when you are simulating a Verilog module, a Verilog code, then all the nets which are not connected either physically or logically. Physically means you have defined a net, but there is no driver to that net, or there is a driver which is currently in the tri-state. So they will all be set to the z state, and since the register variables have to be initialized before you actually start the process of simulation, so all register variables by default will be set to the undefined state at the beginning of the simulation. So actually for correct operation of the circuit, it will be your responsibility to apply suitable inputs so that the register variables are set to a known set of values before you can apply meaningful inputs and get the outputs. Okay. And corresponding to these 4 logic values, Verilog provides a set of predefined logic gates, and or not, XOR, etc. So, we will see the list of gates, but one thing we understand, first thing is that Verilog as a language, it provides this predefined logic gates as the basic primitive. So, it is not something which you are including here, which you are adding to the feature of the language, unlike VHDL. VHDL does not have any predefined logic gate by default, but Verilog has. Okay. And the way the functionalities of these gates are defined, that is quite consistent with these 4 logic values 0, 1, x and z. Just for example, if you have an AND gate, suppose you have a 2 input AND gate, there are 2 inputs and there is 1 output. So, the way it is defined is that it is very easy to understand. You see that if the inputs are 0 and 0, obviously output will be 0, 0 and 1, any one is 0, output will again be 0. Only when both of them are 1, then the output is 1. But if one of the inputs are at 1, the other is unknown, the output will also be unknown, because the output will depend on the value here. But if one of the input is 0 and the other is unknown, then you can definitely say the output will be 0, because it is an AND gate. Similarly, if one input is 1 and the other is a tri-state value, output you cannot say what it will be. So, it is defined as x. Similarly, z and x will generate x. So, in this way you can define the values for the other types of gate. For example, I am giving another example. Suppose you have an XOR gate. Suppose you have a 2 input XOR A, B and F. Okay. Well, the normal truth table of XOR you already know, I am not showing those things, I am showing the other cases. For example, if one of the input is 0, B is unknown, then output will be unknown. If one input is 1, other input is unknown, output will also be unknown. If one input is 0, the other input is a tri-state, this will be unknown. 1, Z, this will also be unknown. So, this XOR is one gate where just in addition to the 4 normal completely specified condition, the other combination will all lead to an undefined value in the output. This is unlike AND and OR gates. For example, in an OR gate, if one input is at 1, then whatever you apply in the other input, the output will be 1, right. So, it really depends on the gate type you are using, and you can define the functionality like this. So, in the language Verilog, this functionality is already defined in this way, so that during simulation you can get consistent behavior. Okay. And the gate types which are supported are these. These are the primitive logic gates which you can include in a Verilog module through instantiation: AND, NAND, OR, XOR, NOR, XOR, XNOR, NOT, buffer. Buffer is just like a driver, it does not invert the logic value, and as you can see, the convention is that the first parameter is the output, the next parameters are the input. For example, in the first case, the inputs will be in 1 and in 2, the output will be out, right. So, you can have all the basic gate types available as part of the language. These are the normal gates where the outputs are not tri-stated. In addition, you can have a set of tri-state buffers also, which you can use in your definition. There are 4 types: buffer if 1, buffer if 0, not if 1, not if 0. The meaning is like this. The first one, this is buff if 1. This says that the input of this buffer is in, this is a non-inverting buffer. So, there is no inversion, the output is out, and it will be enabled if the control is at 1. So, it will be like this control, but in the second case buff if 0, this situation will be like this, in, out, and the control will have an inversion out here. This is buff if 0. The last two cases are similar, just instead of a buffer there is an inversion there. These are actually inverters, right. So, these are the primitive gates which are available to you. You can use them in your design, you can instantiate them, you can create any netlist of gates. Okay.
So, the control is in the other state, it's a high impedance.
Control by definition must not be in the high impedance. If it is in the high impedance state, the output will be X.
So, if it's in the other state, like if it's 0, if it's 1 for
Okay, if it is in the other state, output will be tri-stated. Just to enable it, you will have to make it 1 or 0, and if it is in the other state, it will be tri, output will be Z. So, these 4 gate types, these all have output tri-state control. Okay, fine. Now, let us note a few points. See here, for all the primitive gates that we have just now seen, the output of the gate that must be connected to a net. That is how we had given a few examples earlier, that whenever you have a gate, that gate must drive some net which may be an output or which may drive another gate. Now, the input ports for each gate, the input port, the inputs which are coming, that can again be nets which are coming from the outputs of some other gates, or they can be register type variables which are possibly coming from some register or flip flop or latches. So, the input ports to a gate can be of net type or it can also be of register type. But one thing to remember, register type variable does not always mean that it will be synthesized into a register. Well, it is most likely to be synthesized in a register, but in some cases, as we shall see, that the translator or the synthesizer can do some optimization where the register can be done away with, register is not required. Okay, fine. So, this primitive gate, as I have said, they have a single output by any number of input. See, in the examples we have seen, like here, the gates, all of them have 2 inputs, but you can also have a gate declaration, say AND, which will have out an output, and for example, there are 4 inputs. So, you can use any number of parameters you want. Verilog does not put any restriction to that, but to be realistic, you should limit the number of inputs to a gate. Typically, we do not use gate fan in greater than 4, because if you try to use gate fan in more than 4, the delay of the gate goes on increasing. So, that leads to a problem. So, the primitive gates, as you use them in your design, they will obviously have a single output, but they can have any number of inputs. And as we shall see, this is again used solely for the purpose of simulation, not for synthesis, that you can specify a delay with each gate or with each component you use in your design. See, once you have this delay specified, then you can interpret your result of simulation, that after this much time the output should change state. You can see the timing diagram, for example, and see that it is really changing after that time, right. So, this delay specification is used only for simulation, and when you are doing or carrying out a synthesis, synthesis simply ignores those delay specification commands, because synthesis is carried out by you can say a software tool which will be targeting some target libraries which is already there. Now, the libraries contain some gates or other components whose delays are already known, pre-specified. So, user cannot give the delay. Suppose you are trying to target a design say to CMOS technology. Now, in CMOS technology in the library already the gates will be available as complete layouts. So, once the gates are available in that form, the exact physical and electrical characteristic of those gates are already known. So, the delays are already known, you cannot specify anything. So, as soon as you pick up that gate from that library, the delay gets specified automatically. Okay. Yes.
First line, so you said the output ports must be connected to a wire, net over wire.
Yes.
Yesterday we said that the input and output ports are.
No, output port means of a gate. I mean, output port means the output of a gate.
So if the module is itself a gate, then the output port has to be right.
No, as I said that by default is a register, but the translator sometimes can replace a register by a wire if the register is really not needed. So, unless you have some clocking, there is no need to hold the value in a register and then forward it. Okay. So, unless you have explicit clocking, this will be translated into a net, but otherwise it will be a register. That is what I am saying. I have not talked anything about clock as yet, that is why I am making this statement. Okay, now let us give an example where you can specify these delays. Okay. This is a very simple example of a Verilog module. Just ignore the first line for the time being. I will come to this first line. This is a module which realizes the exclusive OR function as connection of NAND and OR gates. So, if you look at this netlist, what it is, there is a NAND gate which takes A and B as the inputs, the output is T1. There is another AND gate which takes A and T1. Okay. So, there is an AND gate, one input is T1, other input is A, this gives T2. There is another AND gate which takes T1 and B, T1 and B, this is T3, and there is an OR gate which takes this T3 and T2 and generates F. Now, means if you evaluate, you will find F is nothing but the exclusive OR function of A and B, just we have implemented it in this way. Okay. Now, otherwise the specification is fine. F A B are the parameters, A B are the input, F is the output, T1, T2, T3 are the internal signal nets which have been declared as wires. But you observe here that we have specified some number just alongside these modules we are instantiating, hash followed by a constant value. Now, this constant value indicates the delay in some time units. So, this hash 5 actually means 5 time units of delay. Okay. So, well, you can specify the same time unit, or you can specify any variable time unit for the different modules you are instantiating, for the different basic components you are instantiating. You can have 1, 2, 3, anything you can give here. Fine. Now, these numbers you specify are just numbers, and that number will get multiplied by some basic time scale, you can say, in order to get the actual time. Now, that actual time is specified by the first line. Now, again this first line is used only for simulation purpose. For synthesis, this does not make any meaning, does not make any sense. See, reverse quote time scale 1 nanosecond / 1 nanosecond. This is a typical statement. Now, let us see what this really means.
Sir,
yes.
here the F is a register type, no? The
F is a register type, you really do not know, because this module F might be going to another gate in another module. In that case, you really do not need a storage element here. That depends. We have not explicitly specified. It depends on the context in which you are using, that whether it will be mapped.
Output of a gate can also be a rect.
It can also be a register, it can also be a net. It depends on the context you are using. Yes, true. Time scale is a Verilog keyword. Yes, now let us explain what this. Reverse code.
It has to be used with the reverse code, or
it has to be used with the reverse code. Yes. So these are basically the simulator directive. The simulator directives all begin with a reverse code. Okay. So let us see that what this means, reverse slash time scale. The general syntax is reverse slash time scale, then you specify reference time unit, then a slash, then you specify something called time precision. Just an example, suppose I specify reverse slash time scale, say 10 nanoseconds slash 1 nanoseconds. This will actually mean that, say here you again look at this, we are specifying delays like this. Suppose in a specification somewhere I give NAND hash 5 then something. Now this hash 5 will actually mean 5 multiplied by 10 nanoseconds. This will actually mean 50 nanoseconds, but the resolution with which I can specify the delay is this. I can specify 5.2 also, but if I specify 5.23 then this 3 will be ignored. The first number represents the reference time unit with which the specified numbers will get multiplied. The second one represents up to how many decimal places, or means what is the precision with which you can specify this time. Right. Now in this example we have given both of these to be the same, 1 nanosecond and 1 nanosecond, which means that we will be specifying only integer values. Okay. So the purpose of the time scale command is this.
One represents after how many decimal points we can represent?
See, the ratio 10 divided by 1, it is 10. That means we can represent up to 1 decimal place. But if it is 100 picosecond, for example, 10 nanosecond slash 100 picosecond, then you can represent up to 2 decimal places. If it is 10 picosecond, we can represent up to 3 decimal places. Okay. Well, now let us come to some of the hardware modeling issues. Now here we have seen some examples of some modules. We have seen that we can calculate values in some statements that can be an assigned statement, or in one example we have seen that we can use something like an always block. Inside the always block we can also do some computation. We had seen that count equal to count plus 1 something. So we are computing some value. Now after computation the value must be held somewhere. Okay. Now in Verilog, depending on the types of the variables and the way you are using them, the values computed can be stored temporarily, I mean either in a wire or in a flip flop or in a latch. This wire is the typical scenario when you are modeling pure combination logic. There is no storage element, the value is temporarily stored in our, well see here we say it is temporarily stored solely from the purpose of simulation, but in the actual hardware implementation you are really not storing anything in the wire, it is just the signal is propagating from one gate to the other. But when you are simulating, your time will be advancing by units of time which may be equal to the gate delays. So after this much gate delay, the output of the gate will get a value. That value will be retained logically till the next time unit comes. So, in that sense we say that the value is stored or retained, okay. But actually it is not stored in any register or any storage. And if you want to really store the value somewhere, you are not needing it now, you will be needing it sometime later, you need to store the value, you need to have either a flip flop or a latch. Well, the difference between a flip flop and latch, you know, the flip flop is triggered by the edge of a clock and latch is typically enabled by the level of a signal. If it is low or high, the latch is enabled, otherwise it is not enabled. Okay. Now, you recall that a variable declaration in Verilog, whenever you define a variable, it can be either of the net data type or the register data type. Now, looking from the point of view of the hardware implementation of these, here whenever you define a net or a variable of type net, these will invariably map into a wire. This wire is not the wire data type, I mean a physical wire. They will be mapped into an interconnection, simple interconnection, interconnecting wire. There will be no storage. But as I mentioned, register data type, whenever you are using it, the after synthesis it can map either into a storage cell or it can also map into an interconnecting wire. This depends on the context you are using. We shall be looking at some examples later. You will see
like
that
you were saying in optimization,
yes, some kind of optimization is done, that the translator can easily find out that you really do not need to store this value somewhere.
so then it will use a wire.
It will use a wire in that case. But if it cannot, if it finds out that the value has to be retained for certain input combination, that means it will have to store it somewhere. So, in that case it will map or synthesize it into a storage cell. Okay. So, it really depends on the context how you are using the variables. Let us take some example, let us see some examples. This is a simple example which shows that how a register type declaration can map to a wire. See, the first thing is that any signal you can define as a register type variable if you want. And here one thing you must be thinking that sometimes we are using assign, sometimes we are using this always. Well, we shall be clarifying these differences later, but
What is it equal to? Equal to is same as?
Equal to is assignment, but there are some differences. We shall be looking into the nitty-gritties of this a little later. But one thing you just remember, in the always block, the variables you are assigning to, they must be register type variables. But in contrast, in an assign statement, the variables you are assigning values to, they are net type variables. This is one difference. Okay. So, you look at this description. This is just a dummy example, it does not do anything meaningful. ABC, F1, F2 are the parameters, ABC are the inputs, F1, F2 are the output, and we have defined ABC as wires explicitly and F1, F2 as registers explicitly. This statement always at the rate at A or B or C, this statement actually means is that the block that is inside always, that will be evaluated if this expression changes value, not true, it changes value. That means either A changes or B changes or C changes, that means there is an event. This is some kind of an expression I am specifying, this is sometimes called a event expression. So, the whenever there is an event out here, the block gets evaluated. You recall in the example we gave earlier, here in the event expression we had written at pause edge clock. Pause edge clock is the event, there is a positive edge on the clock, then we evaluate. But here there is no clock. So, here we are perhaps talking only about combination logic, but we are saying that if A or B or C change, only then you evaluate. But one thing you again understand, this kind of statement I am making, this can possibly make sense only to the simulator, But when you have a hardware implementation, for example, you have this is AND and NOT, it is a NAND gate. So, you have a NAND gate with the inputs A and B, this is XOR, this is F1, this gets into an XOR gate, the other input is C and you get the output F2. But once you have a hardware implementation, you really cannot tell the hardware, that means only when A, B or C changes you evaluate, the evaluation will be continuous. There is no particular time or particular point in which you say, well, you can argue that the internal values cannot change unless one of the input changes. That is true, but it is a continuously driven thing. Just you cannot say that you start the evaluation, there will be a continuous evaluation which is going on if it is a combination circuit. Okay. Now, the synthesizer can look at it and find out that, well, number one, there is no clock involved, there is no triggering by an edge. It says whenever the values changes you evaluate, and inside it says that, well, there is a data dependency between these two statements. So, it will possibly synthesize it like this, and it will also find out that you really do not need to store or hold F1 in a latch or a flip flop. This can be implemented as a simple interconnecting wire, right. So, this is one simple example where this reg type variable can also map to wire. See, in fact, here you are trying to model combination circuit only, and the synthesizer is intelligent enough to detect this and map it into a non storage solution. Okay.
So, regs map to the register only when there is a clock circuit, so what?
Not necessarily, we will see some examples. Clocks are one thing, if there is a clock, it has to take place at the edge of the clock, there has to be register, but there are other cases also. You look at this example, this is apparently a problem case. Well, this problem case, why I am calling it a problem case? See, the first part is the same as in the previous case. The only thing we have done, you just look at the previous example, the only thing we have done, we have interchanged F1 and F2, these two lines. See, one thing you understand,
Even the expression for
yeah, right, this should be, sorry, this should be C, this should be C, sorry, fine. So, one thing to understand, when we are writing statements inside this block, these statements are supposed to be executing concurrently, this is the semantic. But when the user is writing these statements, well, perhaps it is playing on the back of my mind that the first statement, when I am writing F2 equal to F1 XOR C, this F1 is the last value of F1, then I am calculating a new value of F1. So, actually when a user writes the code, the user can perhaps make that mistake that, well, I am actually wanting the F1 of the previous step and then I am calculating a new F1. But Verilog will not do that. Verilog will simply carry out a data dependency analysis assuming these statements are independent, and it will synthesize the same circuit as in the previous example. This will synthesize the same circuit as in the previous example with a simple interconnecting wire. But what the user was thinking, if you had to implement that, then you needed a latch or a register, because in one step of the iteration you are calculating the value of F1, in the next step of the iteration, when one of the input changes, you really do not know when the input is changing. The input may change 1 hour later, but you will have to hold the old value of F1 till that time occurs. So, actually what the user apparently thinks and what the Verilog translator does, there can be a conflict if you are not very careful about it. But of course, if you know how the translator works and how the translator will deal with this situation, then it is fine, but there is chance of making mistake out here. Well,
New value of F1 will be computed and then it will be used for computing F2.
That will depend on the delays.
Old value of F1 won't be used
old value F1 will not be used.
because they are executed parallelly.
Yes, you see this block will be executed whenever one of the inputs change. So, what I am saying, whenever one of the input changes, it is not the old value of F1 which is used to calculate F2, it is this value of F1 which is used only. Okay.
So that in a cascade system, the new value is used for the like this system. If you can show the diagram, sir.
Yes.
Like yesterday we were talking about the cascade system.
Huh.
So F2 will always use the new value of F1, sir.
F2 will always use the new value of F1.
No
Yes.
matter if we use assigned or
Because here the semantic says that inside a beginning block all the statements are executing concurrently.
so if they're occurring concurrently, then we should use the old value. Or if it's using new value, that is sequential.
Concurrently means again I am saying that this is getting synthesized into a hardware circuit like this. So, concurrently means you can say that that F1 is getting a new value here, F2 is getting a new value here at some point in time, but after a time equal to the gate delays, the value of F2 will again change because this value has changed.
So the gate delays will matter.
Yes. So, it is not only depending on A or B or C, depending on the gate delays there will be a chain of changes which goes on.
So if you wanted the old value, you would explicitly have to mention a latch or something.
Yes. If you required to use the old value, you would have explicitly specified in a different way. That we will see how we will specify that.
So the chain of the value of F2 will depend on the delays also.
Chain of value of F2 will depend on the delays of the gates as it goes on. So, that when you simulate this, you will see in the timing diagram that after some delay the values are getting changed or computed. Yes. Well, now let us look at an example where a latch or a flip flop gets explicitly inferred, synthesized. Double slash means a comment in Verilog, this you can give anywhere. So, this is the specification of a simple latch where you have a data input, you have a data output and you have a load signal. Data and load are inputs, D out is an output. Now, if you look at the specification, this also uses an always. It says always load or data. So, unless data or load changes, there is no need to make any computation. So, this computation will take place whenever either data changes or load changes. Now, you look here, it says if not load, this is active low, we are saying this is active low. If load is 0, then data gets into T and D out equal to not, well here there is an inversion out here actually. In the output also there is an inverter. So, it says if the load is 0, then the data gets stored into a T. So, actually if you draw the diagram in a different way, the latch output is T and after T there is an inverter, that is your D out. So, if load is 0, the data gets latched into T, after that not of T gets assigned to D out. But if load is not 0, then whatever the value T was, this if will not be executed, then whatever the value of T was there, not of T will go out, right. So, if the load is not active, just the data changes, there will be no change in the output. Now, you look at this code from a different angle. See, there is an if statement, but we have not specified the actions for all the branches of the if statement. We have said what to do if the if condition is satisfied, is true, but we have not specified what is to be done if the if condition is false. That means the else part of the if statement is not specified. Well, it can mean if.
It is implicitly understood as D out equal to no.
Yeah, but one thing you just try to understand, this can be an if statement, this can be a case statement, whatever. This is a multi-way branch kind of a statement where all the conditions are not specified, but here you are calculating some value t which is get assigned in some other statement outside this if. So, if all the parts of the if statement were specified, then this could have been mapped into a combination circuit. Since you have not specified what will be the value of t if load is not 0, this means you will have to remember the old value of t, because the old value of t will get assigned then. So, a rough rule of thumb is, if you have a incompletely specified if statement or a case statement, this will imply a latch. That means you need to store the values somewhere. But if the if statement was complete, even in the else part you had written some t equal to something, say, then you explicitly know that you check this, if it is true t is this, then t is this, then you go here. So, it will be a pure combination logic. There is no concept of remembering the old value. So, if you have an incompletely specified if statement, it can be a case statement also, we will see these examples later in more detail, then we will infer a latch.
So T is not declared, why it
T should be a wire, T I forgot to declare, yes, you are right, T should be a wire T. It should be a rich T, not wire, rich T, because it is inside the always block. Yeah. So, we shall be looking at more of these examples later, so do not worry, we will see this in more detail. Now, let us very quickly browse through the different operators which are there in the language. These you can use in your coding. The arithmetic operators are very much like C: multiplication, division, addition, subtraction, and this modulus. Logical operators are also same: negation, logical AND, logical OR. Relational operators are also same, nothing to say here. Bitwise operator, bitwise means not AND, OR, XOR, XNOR. Bitwise means if you say A and B, then there will be a bitwise ANDing. Say A is a 4-bit number, B is also a 4-bit number, there will be a bit by bit ANDing, 0, 0, 1, 0, this will be the result, right. And logical operators are used only in case of relational expressions in an if statement, if this and this, like that. Bitwise operators are there, these are also there in C, similar, but what is new out here is something called reduction operators. Reduction operator is something like this. Suppose you have a number A which is a 4-bit number, and I want to do a ANDing of all these 4 bits to generate a single bit. This is called reduction. This operates on all the bits of the word and generates a single bit result. So, it can be AND, NAND, OR, NOR, XOR, XNOR, anything. So, you can have this reduction operator also. You can use this ampersand followed by A, this means reduction. This is how you use this. Shift operator is very similar to what we have in C. Concatenation, replication will show with examples. Concatenation means you can concatenate several different things to create a single bit stream, a single number. Replication, some of the bit stream you can replicate, we will see with examples these two things. These two are new. Conditional again is available in C, okay. This if then else kind of thing, condition, if true then this, if false then this. Now, let us take some examples in which you can illustrate how to use these things. This is one simple example which illustrates some of the operators and also some other concepts. You see, this is an example which takes two inputs x and y and two outputs f1 and f2. X and y are both 10-bit quantities. These are of type wire. f1 is 5 bits and f2 is a single bit, right. There are 4 assign statements. The first assign statement says that you extract a subset of the number x. See, x is a vector whose indices range from 0 to 9. So, here when I say x 4 colon 0, I am extracting the least significant 5 bits of that. Similarly, here I am extracting the least significant 5 bits of y. I am doing a bit by bit ANDing of those two, that I am assigning to f1. These kind of things I can do. Even if I have a big size vector, I can extract any subset of bits from there and I can use it in an expression. Similarly, I can use this thing f2 equal to x2, a particular bit of this x, or not f13, a particular bit of this. So, I invert it and I take a OR. This is a reduction operation. X is a 10-bit vector, I take the NAND of that, bit by bit NAND, all bits I take a NAND operation. Okay. This is an if then else. If f2 is true, then you take these 5 bits, else you take these 5 bits, this way assigned to f1. Okay. So, these are the things you can do in Verilog, which well, if you recall in C you cannot do these things. You cannot extract any arbitrary subset of the language. Of course, there are other languages which are predecessors of C, like there was a language called PL1. There it was possible to do all these things, but in C you cannot do. And you can also have some kind of a vector arithmetic operation, as this example illustrates. See, here we are trying to model a parallel adder. Parallel adder says that we have one input vector, this is a vector in 1, there is another input vector in 2, there is a carry in, and in the output you have sum, this is also a vector, and we have a carry out. This is an adder we want to model, and we are wanting or requiring an 8-bit adder. So, in 1 and in 2 we have declared as 8-bit quantities, sum is also 8 bits, C in and C out are single bit quantities. Now, you look at this line, in 1 plus in 2 plus carry in, this will be the result. Result will go where? Result will go into the concatenation of C out and sum. So, even while assigning I can specify concatenation. This will be an 8 plus 1 9-bit quantity. And so, the result will be computed in 9 bits and that will be assigned to the combination of C out and sum, this 9-bit combination. Okay. So, this is an example of using concatenation in the assignment in the left hand side, and this is again for the purpose of simulation. You assume that this addition will take 20 units of time, right. Now, there are a few other things you should keep in mind, that if in an expression you have z or x, I mean it is not a logical expression, it is an arithmetic expression, you are doing some addition, subtraction, multiplication, division. If any one bit of any one of the operands is either at x or at z, then the entire result will be x. For in case of logical expressions, you have seen that we can use some logic to generate the output values, but for arithmetic expression we cannot say anything, we will straight away say it is x, not known. And another thing is that the logical operator or the relational operator, they all evaluate to binary values 0 and 1. Of course, sometimes logical operators, if the operands are x or z, they can evaluate to undefined, but relational operator less than greater than they define to yes or no. Boolean false is represented as 0, Boolean true is represented as 1. Just like C, you can use them as numbers and use in an expression you can compare if you want.
So logical operator don't evaluate to a z or what sometimes?
Logical operator cannot evaluate to a tri-state. It can't evaluate to a tri-state. Logical operator means this condition is true and this condition is true. It is not an AND gate you are modeling. So just one last slide to show some more examples of assignments. See, here you can do an assignment like this. This is very much like what you can do in C. Right hand side compares if P is equal to 1 1 1 1 4-bit combination. This is a relational expression. This can evaluate to either 0 or 1. This will be assigned to out P. And similarly, if you can write an if statement like this, if load and some condition select equal to 0 1, you can make an assignment. This is right shift, left shift, right shift by 1 place, left shift by 3 places. Assign f equal to ab, this is concatenation. This ab you concatenate, then you assign the total thing to f. Similarly, this is another concatenation, a followed by this 3-bit number 101, then b, whatever it is, that we assign to f. This is also concatenation, x2 this 1 bit, y0 another bit, and a, this you just assign. This is an example of replication. See, within curly brackets, if you give a number, again a curly bracket, within curly bracket you specify something, then that something will be replicated so many times. So, in this example, whatever is the value of a, that will be replicated 4 times, and then that will be assigned to f. This replication and concatenation you can mix up. Binary 1 0 followed by 3 times 0 1. So, 1 0 followed by 0 1 0 1 0 1 followed by whatever is the value of x, that this thing is concatenated and the value is assigned to f.
So in the first one,
Yes.
if P is equal to that, then it will assign to.
No. This is also a valid statement in C, something like that. Of course, in C you cannot write this. This is a relational expression. Double equal to means if P is equal to this.
So that means 1 or 0.
1 or 0. This will evaluate to a single bit value that will be assigned to out P.
And all concatenation statements, f has to be appropriate size.
Appropriate size. This is just for example purpose I have given. F has to be an appropriate size. It must be of the same size as the right hand side. And so.
There was assigned hash 20.
See, hash 20, that is just for the sake of specifying the delay of this statement.
There is no single variable or var in which you are assigning it, cout and sum.
This is an concatenation. I am assigning it to this. Cout and sum, that is implied. Cout is 1 bit and sum is an 8 bit. Total is 9 bit, and the result will come as 9 bits. That will get assigned to these 9 bits. So the MSB will go to cout. So in our next class, we shall be looking at some of the Verilog description styles, slightly higher level description styles, which you will see interestingly, they will be mapping in terms of synthesis into very well known hardware modules. So as a designer, you need to know, that means if I write my code like this will get mapped into a multiplexer. If I do it like this will get mapped into a decoder or something like that. So we shall be looking at some of those design styles in the next class. Thank you.